morning everybody and welcome to NPTEL online certification course on semiconductor devices for next generation FETs, a physics perspective. This is lecture number 16 and the topic of the lecture is MOSFET switch and an amplifier. So let me give you the outline of the talk. We will be working on first of all MOSFET as a switch, right. So to understand basically what we will be looking in this last part of week 2 is give you a brief idea about the application of FET devices, right. Brief idea, maybe a very brief idea, though this requires actually a full semester to teach. However, because of the nature of this course, I'll just give you a brief insight of the application and then we will be quickly switching to other topics. So we will be looking into MOSFET as a switch, then we will look as a MOSFET as an inverter and then amplifier, look at the small signal voltage gain and then maybe have a look at couple of other MOSFET applications. Let us go one by one and then let us see how it works out. So what you know a switch, what is a switch? So a switch is a one which gives you a low resistance in one direction and gives you a high resistance when it is in the off state, right, is exactly the concept of switch which you have in your residences and various places, where you when you switch it on, you basically provide a low resistance path between point A and point B and therefore a current flows, and when you switch it off, it removes that connection between point A and point B, and as a result the current goes to 0 and the resistance is relatively high. From this basic idea of switch, let us look at a MOSFET and see how it works out. So if you remember, MOSFET has a gate, source and a drain, and we also know that when my gate voltage is exceeding the threshold voltage of the device is in the on state, and when my gate to source voltage is less than the threshold voltage, we come into the off state, right. We already know this point from our previous discussion, and that is the reason you see the first point, for what value of gate voltage will the device turn on, and we define that gate voltage to be the threshold voltage. So when the device is turned on, it primarily means that the inversion layer or a large channel layer is between source and drain is formed, which effectively means that the resistance offered between source and drain is very small. So your on resistance therefore is very small when the device is basically in the on state, and off resistance is relatively large in that case. So it is exactly the same way that a switch will work in a conventional sense of it. So who is controlling the switch in case of a MOSFET? It is basically the gate, right. So the gate is controlling the switch. As the gate voltage goes on increasing and crosses the threshold, inversion layer is formed and there is a drain to source current. If there is a drain potential applied, gate voltage going below VTH, therefore it goes in the off state even if you apply a drain voltage, right. Now therefore you will also appreciate this fact that in on state, since your resistance has actually gone down, your RC time constants, which is tau, will be much lower at on state, and RC time constant tau will be much higher at off state. In fact, it might not be available to you at this stage. So if you look at the third point, what limits the speed of the device? The things which limit the speed of any device is its resistance and its capacitance. Now even if I assume that the capacitance of this device is constant, the resistance varies drastically from a very low value to an excessively high value, and therefore the tau value actually goes one very low to very high, right, and that is what the idea is. And we define the frequency of operation is equals to 1 by tau. So a lower tau implies a higher frequency of operation, and that is what happens when you reduce put the gate voltage to a low value. So this is how you can actually make the MOSFET work as a switch. Now if I take a simple MOS device here, this is basically MOS device, do not look at what it is written here, it is basically a enhancement mode N type MOS device. Now when you put 0 here, let us take the first row here, when you put 0 here, if it is an N channel enhancement mode MOSFET, this will be cut off and this V0 will be equal to Vs, because this current, there will be current flow here, there will be IDRD drop, assuming that to be small, I will see that my Vs will full come to this. So, when my device is in cutoff state, right, when the device is in the cutoff state, it ensures to me that the output voltage is latched to my drain voltage, right, this voltage here. And when I have turned on the gate voltage, right, then my Vi equals to 1. When Vi equals to 1, the device turns on. When the device turns on, the output goes to 0 because the current flows now through this path. So, a simple switch, if you look at in that sense, a simple switch is there. It also can be converted as an inverter, because inverter, why? Because when this is 0, this is 1, and this is 1, this is 0, right. And from here you can see that device is acting as a switch here, right. I can as well remove RD, but RD is generally not removed because that is the load resistance which you see in the output side. I can also put a resistance on the source side in order to stabilize it. At this stage we will not discuss any further than this, at least for the source side resistance, right. Now, let us come to the CMOS inverter construction. Let me come to inverter construction and explain to you. Looks complicated, I will explain to you using a simple other figure here, explain to you. So, let us look at a CMOS inverter, right. And this is what it looks like. This is my VDD, this is my output, this is my input, this is my source. So, this is the source, drain, drain, source. So, this is PMOS, right, this is NMOS, this is NMOS, and as you can see here, this PMOS and NMOS are connected in such a manner that the two drains are shorted with respect to each other. So, you see I have this drain are shorted together, and the source of PMOS is connected to a higher potential, and the source of NMOS is connected to a lower potential. That is the general trend or basic way of functioning, right. And the gates of the two devices are connected together, shorted, and input signal is given here, input signal is given here, and the output appears in the output side as it is. The inverter schematic is shown here. This is the diagram of an inverter with a triangle and a bubble in the front. Now, as I discussed with you, when input is equals to, let us say, 0, when input is 0, right, when input is 0, my PMOS switches on. So, there is a capacitor here, right. When the PMOS switches on, a current flows from here to the capacitor, charging the capacitor to a high value, implying that the output is equals to 1, fine. So, this is the condition when input is equals to 0. When input equals to 0, my PMOS is turned on and my VDD is connected directly to the output through this capacitor, and the capacitor gets fully charged and the output becomes equals to 1. So, when input is equals to 0, my PMOS is on and my NMOS is off, NMOS is of course off, and when my input is 1, right, my PMOS is off and my NMOS is basically on. So, when my NMOS is on, why NMOS is on? Because my gate voltage exceeds the value of the threshold voltage of NMOS, right, and I leave it exercise to you why at 0 PMOS will be on, you should be able to do it by now. Now, if this is the condition, then the capacitor discharges through this NMOS. So, I had a fully charged capacitor here, output was 1. Now, if I give a path for the capacitor to discharge, all the charge from the capacitor will flow through this NMOS device to the ground, and therefore, the value of the output will go to 0, right. So, therefore, we refer to PMOS as a pull up device in logic, and we define NMOS as a pull down device. Why? Because PMOS is actually pulling up the output voltage to 1 and the NMOS is pulling it down to 0, correct, and that is the reason we define that to be as pull up. So, this is the basic inverter construction or convention which you see. Let me come to CMOS static behavior. Let me say I have this CMOS inverter, right, and I try to plot an ideal plot of V out versus V in. So, if my V in is V out, then this is how you get it. You will get this explanation all in other course, I am keeping that to minimum. So, this is VDD, this is VDD. This tells me that this is my switching threshold, right, VTH, or name it as it is. and it is different from the threshold voltage of the MOS device. So, it tells me that when my V in is very small, my V out is 1, and my V in is very large, my output is 0. So, it is acting as an inverter, correct. Now, typically if you look at the CMOS inverter, it tells me that it works like almost like a digital behavior, right, obviously, that it gives me a digital 1 when the output input is low, and so on and so forth. Typically if you look at the CMOS inverter, which I discussed to you in the previous slide, if you look at the gate terminal, there is an oxide here, remember, there is an oxide here. So, therefore, very small current will be flowing here because it is an insulator, and that is the reason its input impedance will be relatively very high, right. Any CMOS inverter input impedance will be relatively very high, and that is the reason you see here I have a high input impedance, which will actually improve the fan out of the circuitry. You have relatively small, I should not say no, but you will have small static power consumption here. The output impedance is also very small, right, and it is almost a ratioless logic, because you see once you fix up the W by L ratio of pull up to pull down, you can make your high to low and low to high transitions equal, right, and that will give you a reduced amount of latency. Let me explain to you one thing about noise margin before we move forward. A noise margin is defined as the maximum noise voltage which can be sustained by the inverter. So, if I say the noise voltage is 0.1 volt, it effectively means that if the effective noise voltage at the input side is 0.1 volt, your inverter will be able to reject it very easily and move forward. So, ideally you require to have a high noise margin, meaning that your large noise voltages can be removed, effective noise voltage can be removed by this CMOS inverter. This is a generic sort of static behavior which you see. Let me revisit the MOS device as an amplifier. So, as I was talking to you in the previous lecture, if you plot ID versus VDS for a MOS device. So, these are the values of ID versus VDS for various values of VGS, right. So, what I am giving? I am giving a VGSQ, which is a DC bias, so that it is somewhere in the middle of the saturation region. This pink colored line is my load line, right. This is my load line, which you must be knowing from your basic circuit theory course, where the load line actually intersects with the output characteristics of the device. We define that to be as the Q point. So, this is my Q point here, which you can see, right, and so this is your Q point, this is a quiescent point, and you give a signal around that point, you see your output goes to a larger, peak to peak is much larger in this case. This is the basic idea of amplification. Why is it so? Because the transconductance helps you to convert the current to a voltage. So, any input voltage which you are giving will actually make this MOS device remain in saturation, but work with a higher current or a lower current. A higher current and lower current will entail a lower voltage and a higher voltage respectively. So, you see there will be a 180 degree phase shift between input and output. Between this and this you will have a 180 degree input phase shift, because if you look very carefully, V naught is equals to VDD minus ID times RD. So, when your ID becomes larger and larger, V out drops down, and that is how come ID becomes larger and larger, because when V in actually increases, ID also increases. When both of these increase, the second quantity increases and this overall V0 comes down, right. So, I have a DC load line, I have a Q point available to me, and the transistor characteristic shows me in this value. This pink one gives me the VD sat value, and it is that expression which is greater than equals to VGS minus VTH. This VD sat is VGS minus VTH. So, this is a MOSFET as an amplifier, as you can see. So, let us take a common source amplifier, right. Common source means the source is grounded. Look at M1, M1 is this configuration is a common source configuration, M1 is grounded here. So, when my V in is very low, somewhere here less than the threshold, M1 is basically in cutoff. So, here M1 is cut off because it is lower than the threshold voltage of the device. When it is cut off, this VDD almost appears in V out, and you see the output voltage is V out. As the input voltage crosses threshold voltage, this switches on initially in saturation, and then we will see how it works out. Initially in saturation, why? Because just as it switches on, this is grounded, this value is very large, which is equals to VDD. So, VDS in this case, VDS will be equals to VDD minus 0, and therefore, VDS will be a large value, and therefore, the device here will be in saturation. When the device is in saturation, it draws large amount of current. When it draws a large amount of current, what will happen is the output voltage will start to fall, and that is what is happening, right. The output voltage starts to fall till a point where you enter into V in 1, where it enters into deep triode region of operation. The MOSFET starts to behave then as a resistor. So, basically therefore, in deep triode my RD and Ron will be two resistors in sort of connection shown in the right hand side figure. So, in the deep triode region you have this, and then the current becomes very low in that region. If you look at the small signal model for the saturation region, then you see this is my V in. V in is the input voltage which I am giving, and V1 is basically the effective voltage which is appearing at the input side of my device. So, V in might not be equal to V1, right? There might be a difference between the two, because there might be some voltage drops across the way. This V1 converts to a current which is Gm times V1, where Gm is the transconductance of the device, and you have this Rd which is the output resistance of the device, and V out is the output. This is the output voltage. So, this is my small signal model for the saturation region which you see here, and this is for the triode region. So, this model which you see here is applicable between Vth and V in 1, and this is after V in 1, this is applicable, right. So, and therefore, you see when you are in the saturation region, since the current drawn is very large, my V out which I had already referred to as VDD minus IDRD, if this is very large, right, the ID is very large, then this quantity will be very large and the V out fall will be also very large. So, you see a steep fall taking place here, and then it sort of saturates and becomes much lower after V in 1, right. Therefore, if you want to see the gain here at this particular point, change in V out is 0 almost. So, my gain is very low at this initial stages. At subsequent stages, the gain becomes large as I move along, right. So, this is a basic functioning of MOSFET as a basic amplifier. Now, so when the device M1 is in saturation, I can write down M1 V out to be equals to ID times RD, remember. So, VDD minus RD times ID, this is ID. So, since the device is in saturation, I get write 1 by 2 mu n C oxide W by L V in minus VTH whole square, and therefore, I can also write down that V in 1 minus VTH, which is V out, to be equals to this quantity on the right hand side. As a result, the V out starts to drop down. M1 is in the triode region, and in the triode region, you know, the expression for the drain current changes as compared to saturation region, and the expression is given by this quantity here, right, and it is a function of V out. So, nonlinear function of V out. In deep triode, when V out is much smaller than V in to 2 times V in minus VTH, I get my V out to be equals to VDD into R on by RD. Why? Because now you see, if you go to the deep triode region, this R on and R2 are basically in series, and you are trying to find out the voltage across R on. So, the series resistance will be RD plus R on, and if you want to find out R on by RD plus R on to be the effective resistance across R on, this if you multiply this with the VDD value, you get V out. So, it is almost like a potential divider. It is almost like a potential divider. Why? Because this VDD is being potentially divided by this RD and R on, and therefore, the effective value of V out in deep triode will be given as R on upon RD plus R on, and it will be almost constant because RD is constant, R on is almost constant, and therefore, for all practical purposes I get V out to be equals to R on upon RD plus R on. Now, let us look at this expression here. This gives you this expression, and I will explain this later on, but let us look at this expression. So, if you divide by R on the right hand side, I get VDD upon 1 plus RD by R on, which is an interesting idea that if my R on there, this is my V out. So, if my R on goes on reducing because I am entering into deep triode, this quantity goes on increasing, which means that this quantity goes on decreasing, and therefore my V out goes on decreasing, right. And that is what you are seeing in the previous diagram here, it goes on decreasing here. And if you look at V out, if you put all the values here, you get VDD divided by 1 plus mu n Cox into W by L RD into V in 1 minus VTH. V in 1 or V in minus VTH is also referred to as the overdrive voltage. So, higher is the overdrive, lower is the value of V out, right. Higher is the overdrive basically means that lower is your threshold, higher will be lower is your threshold, V in minus VTH will be a large value, which means that my V out will fall down drastically to a low value. So, a low threshold value will give you a lower V out as such. At this stage we have all neglected the channel length modulation effect. So, my lambda is exactly equals to 0 in that case, right. So, we will not consider, so we are assuming that my device is perfectly flat, which means that, so this there will be no slope in the saturation, which means the output impedance will be relatively very high in saturation in this case, right. This gives you a small signal gain of the amplifier, and I will not go into details of it, how I am deriving it, but typically this is GM times RD. The negative sign here comes because of the fact that output and input are 180-degree out of phase, and therefore I get. So, one way to get a large gain out of an amplifier is that you plug on to get a large value of transconductance. RD beyond a point is not a good idea to increase the value of RD. It affects your area of the device, it affects your other performance of the device. But one way to move ahead is to make your GM as large as possible, right. Make your GM as large as possible. However, GM also has a problem that GM increases to a maximum value with respect to VGS, but also it falls down beyond a particular value. So, you should be very much aware that for what range of the input voltage your GM is remaining constant, right. And this is one of the major problems of designing an amplifier, that I want my voltage gain to be actually independent of my frequency, input frequency or input frequency, but that is not the true, that is not truly the case as we have seen in the earlier case. It is only constant between a set of frequencies. At very low frequencies the gain starts to fall down with reducing frequency, and at high frequency range again the gain falls down with increasing frequency. Where the gain is independent of frequency is the point where we are looking into properly. So, this is the value of AV or the voltage gain which we see minus GM times RD for a small signal amplifier. How do you therefore maximize the voltage gain of a common source amplifier? This is an expression for GM times RD, right. You do not have, so this is VRD, voltage across the RD divided by drain current is basically RD. So, this is your RD, and this whole quantity which you see here is GM. So, if I was just saying to you, when GM is plotted with respect to V in, it first increases, reaches a maximum, then falls down. So, if you are either operating here or here, your GM will be small. So, try to operate somewhere around V in 1 and you will get a much larger value of GM. Similarly, you need to also ensure that your aspect ratio, W by L ratio should also be as high as possible, right. But there are costs you pay for it as far as device is concerned. So, if you look at this expression here, the one way to improve upon AV is to make your Cox large or W by L large, or you make your voltage RD as large as possible. The one way to do it is, most of us do it, is by increasing the value of W by L to make the common source stage amplifier work with the maximum voltage gain in this case. Another example which you will get is basically that this was a common source stage which I was talking about. In the common source stage, if I use a common source, let me show you an example, and this is my NMOS here, this is my input, this is output, right. I have the capacitor here, this is RD, this is C, this is my transistor M1 and this is VDD. So, I have this input given here, right, and this is the output which you see here. Now, one example will be, or one way of looking at it is, can you have, and this is a problem assignment to you as well, can I have another common source amplifier cascaded with respect to the first one. So, the problem statement which I am leaving you to understand is, if this is say CS1 stage, can I have a CS2 stage added to it such that the overall gain will be equals to the gain of CS1 multiplied by CS2, voltage gain of CS2. So, this is the problem statement I am leaving to you, and you might have look into it, look into various books or lectures, and you will be able to find the answer. That if I give you CS1 with a voltage gain of, say, voltage by voltage of 10, I give you a CS2 with a voltage of voltage 10, then I want an overall gain of 100, and therefore you need to cascade these two together. How will you do it? I am leaving this job to you as far as this sort of network example is concerned. Other MOSFET examples are, they are all used in digital logic circuit design and analog design. I have given an example in analog design here and one example of digital circuit design in this case. So, with this, let me recapitulate what we have learned till now. We have learned, at least in this lecture, how can I use MOSFET for analog applications, primarily amplifier. How can I use so I can write down for you. So, we learned about MOSFET in analog domain. Though it requires a whole lecture series in this one, and that is what we have learned in amplifier. And we also learned MOSFET in digital domain, right, and this is basically as a switch and as an inverter. We have learned these two together today, and one example of a common source amplifier has also been explained to you as far as this course is concerned. So, with this, let me thank you, and we come to the end of this lecture, week 2, and thank you for your patient hearing.